have discussed about various performance parameters like efficiencies, right, propulsive efficiency and thermal efficiency and overall efficiency. But question arises, where we will evaluate those efficiencies of an engine? Can anybody tell me? Just to facilitate to answer, I will tell you in the two places one can. For example, if I talk about propulsive efficiency, if my vehicle is in the ground, right, can I evaluate? Or when the vehicle is moving, I will have to evaluate. If you look at the definition of propulsive efficiency, the expression for propulsive efficiency, right, you will find there is a flight velocity, particularly for air breathing engine and also for non-air breathing engine, right. And if the flight velocity is 0, what will happen to propulsive efficiency? Can you look at your notes, what you are getting? It will be having no meaning, right. So, therefore, it has to be evaluated all the efficiencies depending on what you are doing at two conditions. One is static condition, right, and another in the label flight at the particular altitude and particular flight Mach number for which it is being designed. And of course, other places one can, but these are the two which are being used routinely. Now, we will be talking about another parameter which is quite important, that is known as static thrust. Static thrust means like on the ground condition, it is static, it is not dynamic, right, it is not moving, the vehicle is not moving. That means my flight velocity will be 0, right. If I look at the thrust expression what we have derived, it is having two components, right. One is the momentum thrust, other is pressure thrust, and we can assume for the simplicity the nozzle is fully expanded. So, if it is nozzle is fully expanded, then pressure thrust will be 0, P E is equal to P, right, A. So, therefore, it will be 0, and then if the flight velocity is 0, then we will get static thrust is equal to m dot E V E. So, if you look at basically thrust definition is m dot E V E minus m dot A V A, right, or V simply I am using, plus A E P E minus P, right. So, this will be 0 and this is 0. So, we will get static thrust is basically the m dot E V E, right. That means, what is indicating? It is indicating that static thrust will be higher or will go on increasing when the exit velocity or the jet velocity from an engine will go on increasing for a particular air mass flow rate, right. Air mass flow rate will be dependent on what? For an air breathing engine, it will be dependent on the flight velocity, yes or no, and also the cross sectional area of the engine, right. Now, when you talk about this, whether the static thrust you need to have higher or lower, what you need? That depends upon your what? Requirement. Is it so? Because if something is there in the stationary, you need to make it to move. What do you have to do? Initial thrust will be higher, or the force you will have to apply more, static thrust will be higher. If a payload is higher, then naturally I need to have a higher static thrust, right. Is it clear? And if I look at this, static thrust will be dependent on what? Exit velocity or the jet velocity from the engine, and jet velocity will be dependent on what? Like I am putting some fuel, right, it will be dependent on how much fuel is getting consumed, because I am adding energy. It will depend upon type of fuel I am using, that means calorific values. It will be dependent on also the efficiencies, right. What is that efficiency? Thermal efficiency, how good it is, the energy is converted, because we are using thermal energy, right. Am I right or wrong, right. So, therefore, that means how much kinetic energy or the energy being obtained by burning the fuel. So, therefore, we need to look at the static thrust can be expressed in terms of V e exit velocity, m dot f, that is the mass flow rate of fuel, and the heat of combustion, of course, which will be dependent on the kind of fuel you are using. For example, nowadays people are thinking of using hydrogen as a fuel in aircraft engine, right. Although aviation turbine fuel is being used, and now people are talking about using biofuel, biodiesel, not bio diesel, rather bio aviation fuel, right. They are designing it because the fossil fuel won't be there. So, the calorific value will be changing, right, and it will be dependent on the thermal efficiency, because you may burn certain amount of fuel, how good it is in converting to the change in kinetic energy, that we will be looking at. So, therefore, let us look at expression for thermal efficiency, which we have already derived, and keep in mind that this efficiency, thermal efficiency, we have derived assuming that nozzle is fully expanded. So, therefore, P e minus P term is not there, and whenever we are talking about static thrust, the flight velocity will be 0. So, then what I will get? I will get basically static thrust as m dot V e, right, that is by definition is equal to 2 m dot f delta S c and thermal efficiency divided by V e, right. If I assume that certain amount of fuel I am burning, right, for a particular fuel flow rate and particular kind of fuel, let us say for aviation turbine fuel in case of aircraft engine, and the efficiency is remaining constant, which I mean of course may not be, then the thrust efficiency is inversely proportional, or static thrust is inversely proportional to the jet velocity, or what I call exit velocity from the engine. What is indicates? It indicates that whenever exit velocity will be go on increasing, what will happen to the static thrust? Static thrust will be go on decreasing, right, because if V e is in this case is increasing, the static thrust what will happen will be decreasing, right. And when the other way around, if V exit velocity, jet velocity is lowering, like down, and keep in mind whenever we are saying that for a particular mass flow rate of fuel, for particular thermal efficiency and particular kind of fuel, then it is valid. Keep this in mind, okay. You should not get confused with that, okay, I will vary this thing, then I will talk, no, right. So, and therefore, it will be other way around. Suppose I want to have a higher static thrust, I will have to decrease the jet velocity, keeping of course for the same mass flow rate and same kind of efficiency, thermal efficiency and same kind of fuel. Based on this, right, the gas turbine engine can be divided into 3 categories, right. As I told you earlier, that based on the propulsive efficiency, right, people have also divided the gas turbine engine, rather they have innovated 3 kinds of engine to meet their requirement. For example, I want to take some load like a let us say there is a Kargil war, right, I want to take some ammunition from the land to the war site, from interior to the land war site. I will have to carry lot of ammunition which is heavy, right. So, that means I need to have a higher static thrust. What I will have to do then? And also propulsive efficiency should be high. So, I will have to go for a turboprop engine, right. Although the exit velocity will be higher. For example, the turboprop engine, the exit velocity from this engine will be much lower as compared to the turbojet engine, right. And here the what will happen, static thrust will be low, right. That means I cannot really lift, or I cannot have a carry the heavy kind of things, right. But however, I can get a higher thrust, right. If I get a higher thrust, I can move at a faster speed, because flight velocity will be higher. So, it is a compromise you are doing, So, similar way we can get in a middle value, that is the in between, which is being used for the turbofan engines, and the ramjet engine you will get the static thrust. Can you get? you cannot really get a static thrust, right? It is impossible. Why it is so? We will answer that question when we will be talking about ram jelly. What I would observe, I would urge you people to look at this figure, because second time I am showing this figure and you will find that it is quite interesting to look at it. So, we will start this lecture with a thought process from a legendary Sir Frank Whittle, who says the jet engine had, like a phoenix, risen from its ashes. The concept was almost dead, right, and then he, and also with the Mod-01, who is another inventor of this engine, they got it, and now we are enjoying the their ideas and implementation of the engine. So, therefore, if you look at in our culture, it is being talked about to become a diuser, that means second birth, right. You should be like a phoenix, you should leave all your things and become a person of excellence. So, the objective of education is to achieve the excellence in yourself, which is lying hidden in you. So, coming back to this, like as I told, like we have really talked about in the last lecture about what you call thrust expression, and then we move to the various efficiencies like propulsive efficiency, thermal efficiency, overall efficiency. Then we talked about static thrust. Now, we will be looking at another performance parameter, which is known as aircraft range. Why you were interested to look at range? That means, or what is the meaning of aircraft range? For a particular amount of fuel, how much distance it can travel, right, or how the distance traveled by an aircraft can be altered or can be enhanced, because from the fuel economy point of view, right, and also from the ease. Suppose I can have a higher flight, I can use a higher thrust to go at a faster rate, but what penalty I will have to pay for that? Is it optimal or not? So, for that we need to look at the aircraft range. Keep in mind, when aircraft is going, there will be ascending stage, that means it will take off and go in a level flight, particularly the passenger aircrafts, long range passenger aircraft, it will be moving at a level flight in a particular height. Of course, there might be a change, but for us we can assume it to be, right, and then it will be land. So, if you look at the aircraft will be taking off from the ground, let us say this is the ground kind of things, right. This is your aircraft which is lying kind of thing, right, and it will be moving, like it is ascending, and this will be level flight and this will be descending. That means, this is known as a level flight. Keep in mind that this portion is a very small time, and this is for this portion, this is descending, this is ascending phase or takeoff kind of things. So, therefore, this level zone is the highest or the larger amount of time you spend on the level flight, particularly for long range passenger aircraft, right. So, therefore, those portions are not very important, we are not considering. However, in the complete thing one has to, but what assumption? In this level flight, what is really happening when the aircraft is flying level, like at one high altitude in a what is happening? There you do not have much acceleration, right. Here it will be accelerating and there it is decelerating, right, in the descending phase, and then in that case the drag is equal to the thrust, right, and the lift is equal to the weight of the vehicle. So, this is the condition what is being we will be looking at, that means the thrust is equal to the drag in the level flight, and we can write down L is equal to D by L, right. I can basically this is D by L, or in other words it is L by D, right, lift and drag ratio. And what is the lift? Lift in the level flight is basically what? mg. M is the mass of the aircraft, g is the gravity which is acting. So, what we will be doing now is that we will have to basically find out thrust power, how much power is equal to do that, and by definition thrust power is equal to thrust into the flight velocity, right. That means T into V, that is your thrust power, right. This is your thrust power is equal to T into V or into mg V L by D, right. So, what we will have to do? We will have to look at this equation 19 can be modified using what? Using your overall efficiency, because if you look at overall efficiency is nothing but thrust power, ratio of thrust power and the amount of fuel or the amount of heat released, right, due to combustion, due to burning of the ATF, aviation turbine fuel in case of aircraft, but in a rocket engine there might be several kinds of fuel. So, what we will be using? We will be basically looking putting this, clubbing this together, and what I will get in place of TV, I can write down eta overall into m dot f delta SC, right. Then I can write down m dot f is equal to mgv, right, and eta delta SC L by D, right. Okay. So, in place of basically TV I am writing, so it will come out of this. So, what is saying? It is saying that mass flow rate of fuel or mass consumption of the fuel will be dependent on the mass of the vehicle, flight velocity and inversely proportional to the overall efficiency and heat of combustion, of course, the lift and drag ratio, right. If the lift and drag ratio is higher, what will happen? The mass flow rate of fuel or the mass consumption of the fuel will be reduced, which is always, of course, keeping other things same, right. So, then it is desirable to have. So, but the mass fuel flow rate can be expressed in terms of flight velocity. How we will do that? Because if you look at a long range passenger aircraft is there, and once it is on the flight, level flight condition, right, what will be change in that mass? Mass of the aircraft will be changing or not? It will not be changing, because the fuel is getting consumed. So, fuel is getting consumed and it is consumed as a very little faster rate, let us say Boeing, which is carrying maybe nowadays, of course, it is a bigger one, 500 people or 700 people can carry, right, 800 people. So, that means so much of fuel has to be consumed, it is a very big aircraft. So, if it is coming in this case, that consumption of the fuel will be very high and it will be reducing, because you are getting consumed and leaving to the atmosphere freely, right, and polluting it also. Then that mass of the aircraft will be decreasing, right. And so, that means mass of the due to the consumption of the fuel, the mass of the aircraft will be decreasing, because there is no way anybody can go out in the level flight, right. So, I can write down m dot f is equal to minus dm by dt. That means, the mass of the vehicle will be containing passengers, fuel, right, and of course, crew members and other things, aircraft itself mass, right. Those are not changing when it is in level flight. So, I can write dm by dt is equal to dm by ds, that is the range. That means, this distance, what I am calling it as a S, the range. This distance I am calling it as a S is range equal to S, right. So, therefore, I can write down minus dm by ds, and the ds by dt is what? Nothing but your velocity, right, or the flight velocity, and keep in mind that there is no acceleration. So, therefore, flight velocity remains same. Now, what I will do? We will put this over here, this club this equation 20 and 21, and we will get dm by ds is nothing but minus mg divided by eta naught delta SC L by D, right. What we will do? We will now take this out, dm by m, and then other terms remaining constant, because overall efficiency you can assume to be constant, L by D is constant, everything constant including G, okay, because G is at one particular altitude, whatever it will be. So, you can take that, and only then if you integrate this expression, right, we will get S is equal to minus eta naught delta S C G multiplied by L by D ln m I by m f. What is this m I? M I is the initial mass of vehicle, of aircraft, I can say. Vehicle means aircraft, and F is the final mass of aircraft, right, and change in the mass will tell you the range, that is the range. So, if you look at this range equation is known as the Brigade range equation, right, which some of you might be aware, right, and keep in mind this range will be dependent on the overall efficiency, right, and it will be dependent on the heat of combustion, and it will be dependent on L by D, right. So, now what we will be looking at? We will be looking at basically what kind of this range, we can maximize this range, right, and how we can maximize that. We can look at how my overall efficiency is varying with the flight velocity. For example, you might be riding a motorbike, right. Of course, earlier days for fuel consumption there is a green zone, where in your speedometer there will be green zone. If you travel in that range, you will get the least fuel consumption. But if you go beyond that, which of course you can fly at a higher, or you can ride at a higher velocity, but you will have to pay penalty, right, and that is true for the life. Each individual is having their own pace of doing the thing, and if you try to catch somebody, then you will get a stress, right, and that is the problem with the modern life, and that is the same thing with the aircraft, right, and if you look at it, is all natural things, right. So, therefore, one has to look at, let us look at how we can maximize the range or minimize the fuel consumption, right. For a particular initial fuel and final fuel ratio, we will be looking at that. As I told you that overall efficiency will be dependent on what? Flight velocity or not, right, and similarly L by D will be depending on flight velocity or not, yes or no, right. So, the overall efficiency will be depending on flight velocity, but whether it will be increasing or decreasing. Can you look at your formula or expression? So, if you will see, it will be goes on increasing, because if you look at overall efficiency is equal to V E minus V into V, right, and of course, you can say a particular exit velocity, right, kind of thing. So, and delta S is remaining constant, for particular kind of fuel, and F is, you can assume it to be constant. So, then you will find out overall efficiency is goes on increasing, but whereas L by D is maybe little bit change is occurring, but it is remaining constant in the some range of flight Mach number, but after that it decreases and it becomes slowly decreases in case of a supersonic flight. You can note that in supersonic flight which is greater than 1, you will find L by D is very low as compared to the subsonic. This region is the subsonic and this is supersonic from right. Now, if you club this together, that eta L by D, you will find if I just use multiply this and replot it, I will see I am getting that this thing is goes on increasing and reaching a value over here, if you look at, and then it is decreasing, and again of course, it goes on increasing. because this is increasing and this is decreasing. So, finally, it will be increasing. What is indicated? Indicating that the range, maximum range can be obtained whenever you are flying at a subsonic speed of 0.85 around. Do not go by that exactly 0.85, right, but around that if we will fly, then we will get the maximum range for a same kind of fuel or same amount of fuel, you can say, right. So, that is the reason why all the long range passenger aircraft will be in subsonic, not in supersonic. Okay. And when, for example, war or something, you will have to fly at supersonic and you will have to pay penalty for that. Okay. So, that is very important, as I told you, for the life. Whenever emergency is there, that is a different thing, but you cannot make your life as an emergency situation, right, and what we are doing. So, we will have to be careful about that. Now, we will be looking at another parameter, what we call it as a specific thrust. What is the meaning? That means thrust per unit mass flow rate of air. What it indicates? Why should we look at this parameter, specific thrust? It will tell me the size of my aircraft, right, because the mass flow rate of air is there. The specific thrust is small. What it indicates? It indicates for a particular thrust, the mass flow rate of air is higher. If my mass flow rate is higher, what will happen? I can get a higher mass flow rate of air which is entering into engine at a higher pressure. If I will go for higher pressure, then what will happen? All these things, material, I will have to use exotic material, or I will have to use whatever material available at this moment, right, with a more thickness. That means weight will increase, or I will increase my area. If I will increase my area, cross sectional area of the inlet, then the drag will be more. So, therefore, it is a problem. So, size of engine will be higher, lot of problem will be coming. Again, the material cost will go up and several other things will happen. So, therefore, it is very important to have a specific thrust as a parameter. So, generally we should have a what you call the higher specific thrust, right. So, that it will be compact engine and then you will get higher thrust. That is another very important parameter which we will have to look at it, that is thrust specific fuel consumption. As the name indicates, what it says, the amount of thrust produced per unit mass flow rate of fuel consumption, right. And if I multiply, if I divide this by m dot A, if I divide it by dot A and that m dot A divided by m dot A, you will get F, that is fuel air ratio, and other one is a specific thrust, right. But is it there is a very different than what we use in our life for your particularly automobile engines? We use that, for example, mileage, right, and of course, nowadays we are talking about kilometerage, right. That means how many kilometers it should go a vehicle, I mean like in a particularly car or for you people bike will be going per unit per liter of fuel, because the fuel price is going up, that is more important, And there is another important parameter which is not being considered, particularly aircraft engine, of course, not buyer of the automobiles, that is the emission. How badly you are polluting the atmosphere where you are living, right. So, that is not being considered by user, which is very important aspect, and as you people are educated, you must be worried about that, because uneducated people or the business people, they will not be worried about it, right. They are ignorant about it. So, that is very important point. So, the thrust specific fuel consumption indicates the quality of an engine for an aircraft, right, because the cost, as I call it, money or the vitamin M is more important. So, therefore, it is also a very important parameter. So, let us look at how this thrust specific fuel consumption for a turbo engine becomes, that is m dot F. divided by the thrust. We know that m dot A 1 plus F V E minus V. Keep in mind that here the what you call thrust due to the pressure is being neglected, pressure thrust basically. And what you could see here, that means the flight velocity comes into pictures, right. That means this thrust specific fuel consumption will be not only dependent on the jet velocity, but also it will be dependent on the flight velocity, right, and that is also true for your automobile, right. Am I right? As I told you that earlier days there was a range of the speed in which you will get the optimum fuel consumption or the minimum fuel consumption, but after that whether you go at a lower speed, you will have to supply more amount of fuel, and if you go at the higher speed, you will have to also pay penalty of consuming more fuel. And similarly in this case it will be, and question arises where we will evaluate this TSFC, and can I use this TSFC for a turbo shaft engine? Can I use this? Because there we are not producing any thrust, we are producing power. So, therefore, we cannot really use that, because here by definition it is mass flow rate of mass consumption of fuel divided by the thrust. And where we can evaluate this, so that I can compare and see that whether it is good or bad for various kinds of engines, even in the same kind of, let us say turbojet, there might be various manufacturer. I need to look at it, where I should evaluate this. Should I evaluate at the static condition, or should I evaluate at the flight condition? Where? There are two conditions, right? Or I can, it can be, there are various places I can Generally, it is customary to look at the turbojet and turbofan particularly at the static condition, right. And another also is there, some people evaluate at the what you call the design condition, design flight condition, right, altitude and flight whatever it is. So, if you look at some number, typical number I have taken TSFC, that is 0.075 to 0.11 kg per Newton hour, right. Per hour you will be consuming this many kg of fuel, right, for a particular Newton thrust, whereas turbofan is very low value if you look at that as compared to the turbojet. Of course, if you go for turboprop engine, it will be much lower, right. And that is the reason why turbofan being used in the long range passenger aircraft instead of turbojet engine or turbo. Whereas the ramjet you can't really evaluate as static, so you will have to evaluate at certain design Mach numbers and altitude. If you look at, if I take these numbers, some range, it is much higher as compared to any gas turbine engines, okay, turbojet, turboprop, turbofan, any one of them. So, you should keep this in mind, and for, as I told you earlier, the TSFC for turboprop and turbo shaft engines becomes basically what you call brake specific fuel consumption, we call it, right, and that is m dot F by the shaft power, and this brake specific fuel consumption is being used routinely for automobile engine as well, right. And but however, in case of a turboprop engine particularly, there will be certain amount of thrust which being produced by the expansion of gas in the jet, right. So, how to take care of that? Because then this is not good enough for the turboprop engine, the BSFC. For the turbo shaft, where the shaft power is being obtained, it can be good enough, but for turboprop engine it is not, because some of the thrust can be obtained by expanding the gas in the nozzle. Nozzle means exhaust nozzle from the engine, right. So, therefore, how we will take care of it? I need to take care of how much thrust power is being produced by the expansion of gas in a nozzle, or for that I will have to use another one which is known as effective brake specific fuel consumption. If you look at it is same as that m dot f divided by p sh, and whereas this thrust is being added, that is the hot jet thrust, right. Okay. The T h, this is the h stand for hot, right, thrust, and V, because the propeller will be producing some thrust, that is taken care by PSH, right, and whereas this will be producing some this thing. So, that will be different. So, this is being used, right. Now, we have looked at various what you call the performance parameters. That means, these are the performance parameters we need to use for evaluating how good engine is, how it is performing, and under what condition. But now, we need to look at air breathing engines and understand what is happening, because if you look at here, we are not worried about what it contains, whether compressor is there, turbine is there, or nozzle is there, we are not bothered, right. It we have taken as a propulsive duct and look at it overall what is happening as a engine. Now, we will be looking at air breathing engine now. Air breathing means which breathes air, not like rocket engine which will be carrying the oxidizer with itself. Now, and air breathing engine can be divided into two categories. One is based on the gas turbine engine power plant, that is known as gas turbine jet engines, and there is another class which is called as a ram jet engine and scram jet engines, right, where it will be devoid of any gas turbine power plant. Gas turbine means compressor, turbine, that is basically gas turbine, right. I mean, which will be of course compressor turbine will be there for your steam as well, water as well, no, okay, water as well, right. Okay. But there we are not considering, we are considering gas. So, therefore, let us look at turbojet engine and what is really happening here. Turbojet engine is having various components. One portion is the air intake, this is the compressor, of course, this is the axial compressor, there is also centrifugal compressors, and but nowadays people are preferring the axial compressor, but some engines are there, particularly turboprop kind of engines which will be using centrifugal. And this is the combustion chamber where you will be burning the fuel and without really loss of pressures, generally people try for it, and then this high high temperature and high pressure gas is expanded in the turbine, and which is again expanded further in the exhaust nozzle to get the thrust. So, if you look at whatever work being derived from this hot high temperature and high pressure gas by the turbine is meant just to run the compression. So, if you look at what is the function of turbine, turbine is just to supply the power to the compression, right, and all the thrust of this turbojet engine is being used or is being harnessed by expanding the gas in a nozzle. Similarly, the turbofan engine, which is little different, and if you look at this compressor, combustion and turbine is known as the gas generator, right, it will be generating the gas, right, and the gas generator is there in this case. Apart from that, there is a fan here, right, and of course, the compressor is there, this is your compressor, right, and this is your what you call compressor is also in this place is there, is a quite big, and then there will be some turbine, right, turbine is there and combustion chamber. Right. So, what I am saying, this is basically is different than that, but what is happening to the fluid which is entering into this engine? Because as the air enters into this compressor, the pressure, its pressure will be increasing, and then when in combustion its temperature will be again increasing, right. There will be also increase in the temperature when it is passing through air or not, through the compressor or not, there will be, even when air intake is not shown properly here, but in this case there will be also increase in pressure so also the temperature. Which pressure? Is it total or static? Static, right? What about total? Actually, in air intake, if you look at, this will be the total temperature, we assume to be remaining constant, because we say that heat losses will be negligibly small, right. So, therefore, the total temperature. So, also the total pressure, of course, it will decrease because of some losses in fluid dynamic from aerodynamic point of view. But however, there will be increase in total pressure in the compressor. So, also total pressure will be almost remain constant, but however, it will be little bit lower, because the objective is to decrease the change in total pressure in the compressor and the turbine. Turbine, of course, the total pressure has to, what will happen? It will be lowering down, because you will extract the work out of it. So, if you look at what I my discussion, objective of discussion, to make you aware that properties are changing, in a very drastic ways. How to take care of this, how to carry out a analysis is very important, and it is quite complex. Not only the properties, temperature and pressure, also the composition of the air is getting changed, particularly whenever the combustion is, whenever it is passing through the combustors, right. So, therefore, that has to be taken care. And if you look at the turboprop engine, the turboprop engine is basically the air will be passing through this propeller, and then air intake, and of course, the compressor and combustion chamber, turbine and expanded in nozzle. You keep in mind that this, whatever the work being harnessed by this turbine will be not only the running the compressor, but also it will be running the propeller through a gearbox, because the compressor is being run at a very high RPM, whereas the propeller cannot really run at that RPM because of several problems, right. So, therefore, we need to use a gearbox, right. Gearbox will reduce the speed and of this coupling, I mean like from the compressor to this thing or the shaft. So, therefore, in this case most of the thrust is being produced by propeller, some of the thrust will be used by being produced by in the nozzle, that is a residual thrust what we call, or it will be very small quantity as compared to the propeller. So, if you look at this kind of, these three kinds of engine we will be discussing, and we will be discussing also the ramjet, right. Let us look at, we need to basically look at this air breathing engine cycle analysis, right. Why we really want to carry out this engine cycle analysis? Basically what we are looking at, we are looking at thermodynamic cycle analysis, right, what you might have studied in your BTech, and also you might have studied in your even thermodynamics, right. And that is the Brayton cycle, and what we will be doing, we will be also looking at Brayton cycle. Why you will maybe around 7 to 8 lectures we will be talking about it, what really we will get. We are not going to get anything, as a matter of fact, am I right? Am I right or wrong? The Brayton cycle, same cycle, like the compressor, then combustors, and then turbine. What we will be looking at, there are several questions comes into picture. How to enhance our thrust? Is there any way we can enhance the thrust, or is there any way we can reduce the TSFC? Is there any way we can enhance our propulsive efficiency and overall efficiency? What are the parameters that will be governing, right? As an engineer, we need to know that, but is it that cycle analysis which is being carried out in your thermodynamic course help you, or can give you directly? It will definitely help you, because that is the basis of all what we will be doing now, but generally it is not being considered there, except looking at thermal efficiency. But what are the parameters that governs is very important, that we need to look at what kind of turbine material we will be judging, and what is the effect of like altitude, what will be the effect of flight velocities, all those things we need to look at it. So, as I told you that it is quite complex, as I told you just now. I mean like that whenever the fluid is passing through this compressor, combustion chamber, turbine, it is undergoing lot of changes. Now, how to handle that? When the composition of air is changing, the temperature is changing, pressure is changing, it is quite difficult to handle. So, we will have to first carry out making some assumptions, right. That means, we can divide this engine cycle analysis based on the level of simplification, because we need to simplify that, right. What we will be doing? We will making some assumption, we will assume the processes are ideal. That means, as if air is moving, nothing is there, like no combustion, no change of properties, and then processes are isentropic in nature, a lot of places like compression, expansion, other things. There is no pressure drop in combustion, all those things will be using, and that is a simplification, and other one is based on purpose. What is our objective? Why we will do this analysis, right? That also based on that we can divide the engine cycle analysis. So, what we will be looking at is ideal cycle analysis, where we will do all those assumptions just now I told, that we will be using the air as if passing through that, and you are adding some heat. There is nothing, no really combustion is taking place, but you are adding heat, that which you are done earlier for your what you call ideal cycle, right, in your thermodynamics course. Then we will be adding those like processes which is actual, right, and then we call it as a real cycle analysis, right. And how we will do that real cycle analysis is very important one. And then we will be looking at parametric cycle analysis, because we need to understand vary those parameters which will be governing the thrust, and then TSFC, and then other efficiencies, other parameters, and play around it and see what is happening, right. We may not have an engine, but we can play around and see that imaginary engine and look at it, like like in your Antaragni people are doing imaginary things, right, imaginary stories, right, okay, or fantasy. So, similarly you will be thinking my engine will be like that, these are the parameter what I need to do. Then once you design the engine, we need to find out that what are these how these parameters will be affecting my thrust and other parameters, right, variables, how these variables which will be affecting my thrust and other performance parameters. That is known as of design analysis, right, like what we call it engine performance analysis, and engine performance we call it as a of design analysis, and this parametric cycle analysis is known as the on design analysis, because we have not designed, but for designing we look at it. So, in this course what we will be looking at, we will be basically looking at these three analysis, which is together, because ideal cycle but I will be looking at ideal and parametric cycle together, right, and then I will be looking at the real cycle also, you might have studied. We will be doing that and adding this parametric variation and look at it. But however, engine performance cycle is not a part of this course. If some of you are interested, you can look at it in some other place, right. So, let us look at how we can carry out this parametric cycle analysis. That means, what we will be doing? We will be looking at parametric cycle analysis. First, we will be considering ideal cycle, then we will be considering the real cycle. So, as I told you, parametric cycle analysis is very important, because here the flight conditions like altitude, flight velocities. When I talk about altitude, it is basically the temperature and pressure at a particular altitude, which will be varying, right. And so, also the flight velocity, how it is varying, how it is affecting the thrust and your other performance parameters, right. That we will be looking at it, and then we will be looking at what are the design limitations. What are the design limitation we are having? Turbine inlet temperature, you do not have material. Of course, if you can develop better material, you can go for a higher temperature in the turbine, because the most critical part of turbine material is in the engine is the turbine material and also the combustor liners, right. So, that is a limitation. How we will live with limitation, how we will do that, and what is the way to how it will be varying this performance parameter we need to look at. And similarly, the component performances, like for example, air take in efficiencies, compressor efficiencies, turbine efficiencies, nozzle efficiencies, how it will be affecting your result, right. That is the way we need to, because we all the time will be trying to improve the efficiency of these components, so that overall efficiency of the engine will be increasing. But how to do that and what is the effect we will be looking at, and this is the very important one, that is the design choices like compressor pressure ratio or turbine expansion ratio and other parameters. So, what I am saying, we are looking at the same cycle analysis thermodynamic from a different perspective, how to design, and when we design we need to know the whole envelope of where it will be, we will be operating, which is the best, and how to choose that and develop a judgment. Judgment is very important, right, not only for the what you call design or the cycle analysis, but also for the life. And what we are lacking today is the proper judgment in life. So, therefore, both are interlinked, and let us look at how to go about it. And objective of parametric cycle analysis, as I told you, it is engine performance parameter, thrust, specific thrust and thrust specific fuel consumption. We will be looking at propulsive, thermal and overall efficiency. These are the parameters, just to, and we will be looking at component parameters like pressure ratio, turbine temperature ratio, turbine inlet temperature, of course, turbine like you can look at turbine expansion ratio, they can be linked, and we will be looking at how this flight environment, or I call it flight envelope, will be affecting the performance of the engine. So, if you look at whole gamut of this thing, we will be looking at in this parametric cycle analysis. I believe or I assume that you may not have this way of looking at the thing, right, because this is a whole things which will be can be used as a very important tool for a designer, right, of aircraft engine. So, we will be looking at that. For that, let us look at general notation, like what we will be using for our analysis. This is a very complex one I have taken. It is a basically turbo fan engines with afterburner. If you look at from 0 to 9, I use the station number for the core engine. This is known as core engine, right. This is a 0 to 1, because 1 will be somewhere here, right. You might be thinking why 0 and there is no 1. If you look at supersonic air intake, if you look at the supersonic air intake will be 0 to 1 and 1 to 2 will be subsonic air intake, right, which particularly for fighter aircraft all those things is required, right. Similarly, 2 to 3, and sometimes some people use here 3.5, because this is your high pressure, what you call low pressure compressor, and this is high pressure compressor, right, this one. And similarly, 3 to 4 is your combustor and 4 to 5 is your turbine, but 4 to 4.5 is your high pressure turbine and 4.25 is your low pressure turbine, and 5 to 6 is your basically you can say kind of a what you call the basically 6 could have been here, like it is a afterburner, and there is a pipe, jet pipe will be there for mixing and other thing, and 7 to 9 is basically nozzle. You might be thinking why, where is the 8? 8 is there whenever you use the convergent divergent nozzle, right. The throat region is known as the 8. Similarly, for the other engine, that is 13 to 9, and this is a standard which is known as aerospace recommended kind of things, standards being used internationally, right. That is why we are using that. So, another thing we need to look at the notation what we will be using, that we will be using basically pressure ratio, and when you talk about pressure ratio of a component X, that is nothing but ratio of total pressure ratio at the exit of component X divided by total pressure at the inlet of component X, right. That means basically if I look at a compressor, it will be basically at the exit, right. In this case, it will be basically P T 3 by P T 2, right. And similarly, total temperature, if I look at for a compressor, if I say this is pi C, then only P T 3 by P T 2, right. That means, this will be the thing. So, total temperature ratio will be basically for x component will be total temperature ratio at the exit of component x divided by total temperature ratio of component x. So, if you look at, we will be using these symbols, right, in place of x for diffuser D, that is basically air intake, and compressor C, and burner and combustor will be using B, pi B, right. For turbine we will be using pi T, nozzle will be using pi N, and fan will be using small m. So, these are the notation which we will be using, and free stream total temperature and pressure ratio can be defined as tau r, that is T T naught divided by T. You know this for isentropic relationship is equal to 1 plus gamma minus 1 divided by 2 m naught square, and pi r is equal to P T naught divided by P naught, the same thing 1 plus gamma minus 1 divided by 2 m naught square gamma minus. And basically, isentropic relationship I have written in terms of flight Mach number. So, we will this will stop over here, and maybe some of the assumptions I will be talking about in the next class, that is ideal cycle analysis, and then we will be talking about ramjet engine to start with.